Welcome back. The first couple pages are the formulas that I'll need for the remainder of this course. The first page are the formulas for hypothesis tests. We've seen most of these formulas before. The first formula with the z, that's for the one proportion situation. The second formula with the t, that's for the one mean situation. The third formula with the z and the p1 hat, p2 hat, that's for the two proportions situation. The fourth formula with the t and the x1 bar and x2 bar, that's for the two means situation. The last formula, we'll talk about this when we get to chapter 12, so we'll skip this for now. At the bottom, the left box, these are commands in R that we'll need. We've seen most of these before also. P norm, Q norm, those are for my Z situation. PT, QT, those are for the T situation. The last row, that's going to be for the chapter 12 stuff, so we'll skip that for now. On the right side, these are commands in Google Sheets or Excel. We'll be using this today, so let me skip this and come back to this later on today. The second page are all my formulas for confidence intervals. We won't be talking about these today, so we'll talk about these in the next lecture. Today, we're going to revisit the two mean hypothesis test. So you may be asking, why do we need to revisit this situation? In the past, anytime you've encountered a two mean hypothesis test, I've always given you the means, the standard deviations, and the sample sizes of the two samples. Today, we're going to take it one step backwards, and instead of giving you the mean, standard deviation, and sample size, I'm going to give you the raw data. And anytime you're given just the raw data, there's two situations that you have to distinguish between. The first situation is this first example. So listed below are heights of a random sample of women and men. So the first row, these are heights of a sample of women. The second row, these are heights of a sample of men. So let's take a look at two of these numbers. 153.3 and this 176.8. And the question we need to ask ourselves is there any reason, based on the description here, is there any reason why this 176.8 needs to go with this 153.3? In other words, is there any reason why this man needs to go with this woman? And all we know based on the description here is that this is just a sample of women and a sample of men. Right? We're not told that they're related in any way. So there's no reason why this 176.8 needs to go with this 153.3. That's an independent situation. So in an independent situation, the values of one sample cannot be matched in a meaningful way with the values in the other sample. And this is different from the next example. Here listed below are body temperatures from 5 different subjects measured at 8 a.m. and again at 12 p.m. Okay, first row, these are temperatures at 8 a.m. Second row, these are temperatures at 12 p.m. And now let's take a look at two of these temperatures. 99.0 and this 99.5. Now, based on the description here, is there any reason why this 99.5 needs to go with this 99.0? And here, the answer is yes. Because based on the way that it's described here, right? So these are body temperatures from 5 different subjects measured at 8 a.m. and again at 12 p.m. So what this is saying is that these two temperatures, the 99.0 and the 99.5, are actually measurements on the same person, right? One at 8 a.m. and then again at 12 p.m. So here, because they're measurements on the same person, these two measurements should go together. So they should be matched. So in a matched situation, the values of one sample can and should be matched in a meaningful way with the values in the other sample. And common examples of the match situation are, there's really two main situations that you'll encounter in this class. One is this situation where we're taking two measurements on the same person. Same person or thing. And then the other situation is where the people in one sample are related to the people in the other. So for example, you may have brother-sister pairs or parent-child pairs. So brother-sister, parent-child. So it's going to be important that we distinguish which is which if we're in an independent situation or a matched situation, because that determines what we do next. Example 1. Do business travelers walk at a different speed than leisure travelers? A researcher measured the walking speed of 12 business travelers and 12 leisure travelers at San Francisco International Airport. The results in feet per minute are shown below. Can the researcher conclude that business travelers walk at a different speed than leisure travelers? Use the alpha equals 0.09 level. The first thing we need to decide is this an independent situation or is this a matched situation? And remember, matched, there's really two main examples of matched situations. When we're taking two measurements on the same person or thing, or when the people in one sample are related in some way to the people in the other sample. So in this situation, based on reading the description here, is this independent or just matched? These aren't measurements on the same person, right? So this is just 12 business travelers and 12 leisure travelers. And nowhere in the problem does it say that these 12 people in the business group are related in any way to the 12 people in the leisure group, right? These are just two separate groups of people. We're not told that they're related in any way. So this is going to be independent. And for independent situations, we run this as a two-mean question. And then just to remind myself, for means, I should be using T throughout the problem. Part A, state the null and alternative hypotheses. Okay, so this is the same as before. We're talking about means and we're talking about two means. So this should be, we should be using the correct symbol for means, which is mu. And there's two of them, so there's mu1, mu2. And what's the symbol that goes in the middle? So we want to show, can the researcher conclude that the business travelers walk at a different speed than leisure travelers? So differs is a not equals. And then H0 always has an equal sign. Part B is the same as before. Draw your picture. Not equals means that this is going to be shaded two tails. And then the shaded area is our alpha. Our alpha here is 0.09. Left and right side together is 0.09. And then your job is to either define the Z star or T star. We're talking about means here, so I'm looking for the T stars. And this is really a area to T problem. An area to T problem area to T for the T situation is going to be a QT, left area DF. So this is a QT. Left area, left and right together is 0.09. If I just want the left, divide that by 2. So left alone is 0.09 divided by 2, which I think is 0.045. Yeah, 0.045. And that's what U feet are. QT has a DF, degrees of freedom. For the two means, two sample situation, you use the smaller sample size, you don't combine them. Smaller sample size and then subtract 1. Both sample sizes are 12, so it doesn't matter which one you use. So 12, and then the DF, degrees of freedom for 12, is going to be 12 minus 1, which is 11. All right, so in R, we're going to do QT, 0.045, comma 11. Negative 1.859. Okay, this is a T star. Based on my picture, I do expect 2 of them. Negative is the one on the left. The one on the right should be positive, 1.859. Part C, find the test statistic. So this refers to the formulas on the front page. We're in the two mean situation, so I'm using this T formula. This formula has a x1 bar, x2 bar, S1, S2, N1, N2. So I need to find an x1 bar, x2 bar, S1, S2, N1, N2. And actually, let me back up a bit. I forgot to label what I mean by ones and what I mean by twos. Okay, so we're talking about business and leisure travelers. So it doesn't matter what you choose for which. Let me choose business for my ones and then leisure for my twos. So my ones are business and my twos are leisure. So the difference here compared to the last lectures is I'm not giving you the mean, standard deviation, and sample sizes. So we actually have to enter this data into, we're going to enter into Google Sheets and then use Google Sheets to find the mean and standard deviations. All right, so let me switch over to Google Sheets. All right, here I am on the single sign-on that you use to log on to Canvas, but instead of going to Canvas, I'm going to go into Google Drive. You can also use Microsoft Excel if you prefer that. So once I'm in Google Drive, I'm going to go to New. Now click on Google Sheets. And I'll name this two means. So it doesn't matter what you name it. And then what I'm going to do is I'm going to enter the data. So I have the business travelers, and then I also have the leisure travelers. So I'm going to enter this as columns. So business, I'll have a business column, and then I'll have a leisure column. And I'll enter the business numbers and the leisure numbers, but I'll enter them as columns. Okay, so I have the data entered. Let me actually zoom in here. And what I need is, I want to find the mean and the standard deviation for the business and the mean and standard deviation for leisure. And in Google Sheets or Excel, the command is going to be, to find the mean, it's going to be equals, average, A-V-E-R-A-G-E, parentheses, and then highlight the column. So I'll highlight the business numbers. Okay, that's the mean for the business. Then I'll move over, do the same thing for leisure, equals, average, A-V-E-R-A-G-E, parentheses, highlight the leisure column. Okay, that's the mean for the leisure. And then for I need the standard deviation also. So the command for standard deviation is equals STDEV, parentheses, highlight the business numbers. And then for leisure, equals STDEV, parentheses, highlight the leisure numbers. And that's going to be the standard deviation for the leisure. And just to point out, when you do equals STDEV, you'll see other standard deviations. Don't worry about all the other ones. The one with the S is standard deviation for samples. The one with the P is standard deviation for population. We're talking about samples here, so we should be using the standard deviation for with the S, which is the same thing as the default one, the one that doesn't have the P or S. STDEV is the sample standard deviation. Okay, don't worry about all the other ones. Okay, now that I have the mean and standard deviations, let me copy this down. All right, back to part C. We're going to copy down the means and standard deviations that we just found. Remember, 1 means business and 2 means leisure. X1 bar is the mean for business. That's 283.083, so rounded to 3 decimal places. 283.083. X2 bar, that's the mean for leisure. That's going to be 254.333. S1, that's the standard deviation for business. Standard deviation for business was 45. Rounded to 3 decimal places, this is going to be 620. S2, that's the standard deviation for the leisure. 30 point, rounded to 3, this is going to be 1110. N1, sample size for my business, sample size for business. There's 12 numbers, so it's going to be 12. N2, sample size for leisure. Same thing, also 12 numbers. That's 12. Now we're going to enter these numbers into the formula for T. So this formula for 2 means. So I'll do this in Desmos. Start off with a fraction. Up top, X1 bar minus X2 bar is going to be 283.083 minus 254.333. On the bottom, square root, fraction. First fraction, S1 squared, is going to be 45.620 squared. Over N1. N1 is 12. And remember, move your cursor just to the right of that fraction and hit plus, so don't put in spaces, because we want the entire thing inside the square root. So if you move it a little bit too far and hit plus, you'll see that the plus is outside of the square root. If that happens, just move your cursor back just to the right of the fraction and hit plus. And then we have another fraction. S2 squared is 30.110 squared. And then N2 on the bottom is also 12. Okay, make sure what you see on Desmos looks exactly like the formula, and then you'll hit enter. And I got 1.822. That's a T. Okay, that's our test statistic. Part D, find a p-value. So we'll draw the picture. Should be the same picture as part B. It's either going to be shaded left, shaded right, or 2 tails. For not equals, it's always going to be 2 tails. And we're going to put our test statistic that we found in part C on the picture. 1.822, that's positive. That should be on the right side. The one on the left, by symmetry, should be negative 1.822. And then our job here is to find the shaded area. That's the p-value. This is really a T to area problem. T to area. T to area for the T situation is a PT, T comma DF. Now, which T do I plug in? So remember, the way PT and pnorm works is you feed it a T or Z, and it's going to spit out the left area. So whatever area is to the left of the T or Z you plugged in. I'm not going to plug in the positive one because to the left of that includes this unshaded part that I don't want. So I do want to plug in the negative 1.822. Because I do want what's left of that. And then the DF, you pick the lower sample size and then you reduce it by 1. Lower sample size here, well, they're both 12. So 1 less than a sample size would be 11. And we're going to do PT negative 1.822. Comma 11. This is 0.048. That's the area to the left of the negative 1.822, which means it's just this left part. So 0.048 is just this left part. I want the area of both shaded areas, the left and the right. By symmetry, the one on the right is also 0.048. And my final answer, either add those two up or take one of them and multiply by 2. I'm going to multiply by 2. So my final p-value is going to be 2 times 0.048. Okay, 2 times 0.048, 0.096. Part E, decide whether to reject or don't reject. The way you decide is you look at your p-value and check whether it's less than your alpha. Our p-value is 0.096. Alpha in this problem was 0.09. Okay. Is 0.096 less than 0.09? If you need to, add zeros to match the number of decimal places. So here we have 3 decimal places. I'm going to add a 0 here. This is really 96 versus 90. It is not less. If it's not less, you don't reject. And remember, you can also decide whether to reject or don't reject using part B, the rejection region. Part B, the boundaries here are, that's negative 1.859, and then that's positive 1.859. And the question is, where is 1.822? Is it in the shaded rejection region, or is it in the unshaded region when we don't reject? 1.822 should be just to the left of this right 1.859, which would put it in the unshaded area, which is telling us to also don't reject. So that's a good way to check your answer. And then part F, the sentence at alpha equals, state your significance level, it was 0.09. There is or is not enough evidence because we did not reject. There is not enough evidence to conclude that, and then state H1 as a sentence. Or go back to the question here. So we're trying to conclude that business travelers walk at a different speed than leisure travelers. So there is not enough evidence to conclude that business travelers walk at a different speed. Example 2. Researchers at a college wanted to determine if classrooms contain less bacteria in the spring than in the fall. 8 classrooms at the college were randomly selected. Researchers measured the amount of bacteria in each classroom in the fall, and then measured the same classrooms again in the spring. The measurements in bacteria per cubic foot are shown below. Can the researchers conclude that classrooms have less bacteria in the spring than in the fall? Use the alpha equals 0.08 level of significance. First question we need to ask ourselves is this a independent or is this a match situation? Okay. Ask yourself, is this one of those 2 main match situations, which are are these two measurements on the same person or thing, or are the people in one group related somehow to the people in the other? So read the description again carefully. It says, researchers measured the amount of bacteria in each classroom in the fall, and then measured the same classrooms again in the spring. So these measurements are measurements on the same classrooms, right? Once in the fall and once in the spring. So these are two measurements on the same thing, which means this is going to be matched. And for matched, we're going to run this as a one mean. Okay, which differs from independent. For independent, remember, we ran it as two means. Okay, for match, we run it as one mean. And then just to remind myself, for means, I should be using t's throughout this problem. Now, what do I mean by one mean? So if it's matched, what we're actually going to do is we're going to subtract. We're going to find the difference and subtract. So 8.4 minus 8.1 is, I think, 0.3. 11.3 minus 12.5, so quickly, negative 1.2. So don't do this by hand. We're going to do this in Google Sheets. So the idea here is if it's matched, we're going to combine the two samples together by subtracting them, and then we'll deal with the one set of numbers, the differences. Okay? So let me switch over to Google Sheets and enter this and then show you what to do. All right, back in Google Sheets, let me scroll down so that we have some space here. And I'm going to enter the data. So we have the fall data and the spring data. And I'm going to enter them as columns. All right, so I have the data entered. And because this is matched, what we want to do is subtract. Subtract the fall minus the spring. So I'm going to create a new column called differences, where I'm going to subtract 8.4 minus 8.1, 11.3 minus 12.5. And the easy way to do this is to set up that first box. So anytime you want Google Sheets to do a calculation, you always have to start off with equals. So equals, and I want to do 8.4 minus 8.1. So I'm not going to type that in, I'm going to click. So equals, and then I'm going to click 8.4 minus 8.1. And then I'll hit enter. And then for the rest of the column, all I need to do is, you can actually say, click yes on the suggested autofill. I'm going to do this the other way, which is to move my cursor to the bottom right until I see a plus sign, and I'll click and drag that. And all we're doing here is we're copying that first box and then pasting it the rest of the column. You can also use the autofill suggestion. All right, so what Google Sheets did for you is subtract all of these for you. And we're just going to deal with the one column, the differences column, because we're treating this as a one sample test now. So all I need to do is find the mean and standard deviation for that last column. So to find the mean, once again, it's start off with equals. Anytime you want Google Sheets to compute anything, start off with equals. To find the mean is average, A-V-E-R-A-G-E, parentheses, and then highlight that last column. And then to find the standard deviation, equals STDEV, parentheses, highlight the last column. And now let me go back and write these down. All right, back to example 2. Let me write down the mean and standard deviation that we just found. So because we're dealing with just a single sample, one mean here, I should just have one mean and one standard deviation and one sample size. So the one mean is round to 3 decimal places. This is 1.538. The standard deviation, 2.651. Okay, and that was from Google Sheets. And then the sample size, we'll just count. There's how many differences are there? There's 1, 2, 3, 4, 5, 6, 7, 8. So 8. Or you could have gotten it from the problem. There's 8 classrooms. Okay, part A, state the null and alternative hypotheses. We're talking about means here, so we should be using the mean symbol. And because we're talking about one mean, it should just be a single mean symbol. And for the match situation, we're always comparing it against 0. Okay, H0 is always easy. It's always equals. Okay, H1 is a tricky one. Okay, let me show you the cheating way to do it first, and I'll explain to you the correct way. So the cheating way to do it is, for match situations, I recommend enter the data, find the differences, find the mean, and then find the standard deviation and sample size. If the mean is positive, the symbol here is probably going to be a greater than symbol. If the mean ends up being negative, the symbol will probably be less than. Okay, so let me say that one more time. For the match situations, enter the data, subtract, find the differences, and then find the mean of the differences. If it's positive, the symbol here will probably be greater than. If it's negative, it will probably be less than. Okay, so here, 1.538, it's positive. It's probably going to be greater than. Now, the reason why I say it's tricky is because if you read the question, it says, can researchers conclude that classrooms have less bacteria in the spring than in the fall? So if you kind of just latch on to the word less, you may be tempted to say less than here, right? But it's not. It's going to be greater than. And the real reason is because what we're really doing here is I have fall and spring, right? So fall, spring. Now, this phrase, less bacteria in the spring than in the fall. What does that mean? What symbol will go here? Less in the spring. So the spring is less, which means the correct symbol that goes here should be that, because that is saying spring is less than fall, which is the same thing as saying fall is greater than spring. Okay, so this is the correct symbol based on this sentence here. Less bacteria in the spring. So the spring is less than the fall. Now, what we're actually doing here is we're moving everything to the left side. So doing algebra, moving things to the left side. So what we're doing is we are subtracting the spring to the left side. Now, the left side now is fall minus spring. Which is exactly the differences, right? We got the differences by doing the fall minus the spring. Fall minus spring on the left side. On the right side, spring minus spring is 0. And that's why it's a greater than, right? Fall minus spring is this mean. So we're actually, to be correct here, we're finding the mean of the differences. So usually in most books, you'll see this mu sub d, because we're saying that the mean of the differences is greater than 0. So fall minus spring is the differences, and we're saying it's greater than 0. Greater than 0. So even though the question, there's the word less, don't get tricked by that. Go through the process, find the mean of the differences. Right? If it's positive, it'll be greater than. If it's less than, if it's negative, it'll be less than. Okay? Or go through. This is the correct reasoning you're supposed to use here. And that's why it's greater than. Okay. Part B, find a critical value and rejection region. So we'll draw the picture. This will either be left, right, or two tails. Greater than, it's going to be two-tailed. Greater than will be to the right, shaded to the right. And the shaded area is our alpha. Our alpha here is 0.08. And your job is to find either the Z star or T star. We're talking about means, so we'll be finding the T star. This is an area to T problem. Area to T. We should be doing area to T. For a T situation, it's a QT left area DF. So QT. Left area. 0.08 is not the left area. 0.08 is the shaded one, which is to the right. I want the left, which is the other side, to get the other side. do a 1 minus. So we'll do a 1 minus to get the other side. And I think that's going to be 0.92. And that's what we'll feed R. Qt has a df. Degrees of freedom is 1 less than the sample size. Our sample size here we said was 8. So 1 less would be 7. And then we'll do a Qt 0.92 comma 7. Now, based on my picture, because it's shaded to the right, I do expect a positive T. And I do get a positive T. 1.572. Okay, that's a T star. Now, if for some reason you got a negative answer, what probably happened was you forgot to do a 1 minus on the 0.08, which is fine. You'll get a negative answer, just remove the negative from it, and you'll get 1.572. Okay, so make sure to match your picture. Part C, find the test statistic. So this is we're running this as a 1 mean, which means we'll be using the 1 mean formula, and that's going to be this one. So we have an x bar, a mu 0, an s, and an n. So x bar, mu 0, s, n. Okay, x bar, we found already, that's 1.538. Mu 0 is the mean that you use in H0, so H0 was 0. S, standard deviation, 2.651. N, sample size, 8. And then plug this into the T formula for a 1 mean, which is this one. All right, so in Desmos fraction, up top, x bar minus mu 0 is going to be 1.538 minus 0. On the bottom is a fraction. Up top, s, 2.651. On the bottom, square root of n, which is 8. Okay, make sure it looks exactly like the formula for t. And I got 1.641. Okay, that's a t. Part D, find a p-value. We'll draw our picture. Because it's greater than, this should be shaded to the right. Put your test statistic on your picture. So I did expect something to the right. So it's positive. All right. Our job is to find a shaded area. That's the p-value. So this is a t to area problem. T to area is t to area for a t situation. It's a pt t comma df. So pt, t is 1.641. df, so 1 less than the sample size. Sample size was 8. 1 less would be 7. All right, pt, 1.641 comma 7. 0.928. Okay, so I already know that that's not the final answer. P-values should be pretty small, and that's because PT spits out the left area, so it always gives you the left area. This 0.928 is a left area, but I'm not looking for a left area, right? I'm looking for the area to the right, which means I'll need to do a 1 minus here. Okay, so 1 minus 0.928. Uh, 0.072. That looks more correct. Part E, reject or don't reject. We're going to take our p-value and check whether or not it's less than the alpha. P-value is 0.072. alpha 0.08. Right? If you need to add zeros so that you match the number of decimal places, let me add a 0 here to make it both of them 3 decimal places. This is really 72 versus 80. It is less, so if it's less, you should reject. And let's double check using part B. So part B, the rejection region, this boundary is 1.572. And the question is, where is 1.641? Is it in the shaded area, the rejection region, or is it in the unshaded part? 1.641 should be slightly to the right of 1.572, which would put it in the shaded rejection region. So that tells me that we should reject, which confirms. Part F, the sentence. At alpha equals, it was 0.08. Level of significance, there is or is not enough evidence. Because we did reject, there is enough evidence to conclude that, and then state this in form of a sentence, or go back to your question here. Classrooms have less bacteria in the spring than in the fall. For the remaining examples in this section, let's just go through and decide whether it's independent or matched, and then write down the correct H0 and H1, because I think that's the hardest part. Example 3. A new post-surgical treatment was compared with a standard treatment. 7 subjects received the new treatment, while 7 others, the controls, received the standard treatment. The recovery times in days are given below. Can you conclude that the mean recovery time for those receiving the new treatment is less than the mean for those receiving the standard treatment? First question we need to ask is this independent or matched? And the question you should ask yourself is this one of those 2 common match situations? So the 2 common match situations are 2 measurements on the same person, or the situation where the people in one group are related somehow to the people in the other group. Okay, so if we read this carefully, it says 7 subjects received the new treatment, while 7 others received the standard treatment. So these aren't measurements on the same people, right? So it's 7 people in the treatment and then 7 other people in the control. So this is definitely not going to be the situation where we're taking 2 measurements on the same person. And it doesn't say anywhere in the problem that the people in the treatment are related in any way to the people in the control. It's just 7 people in treatment and then 7 other people in the control. They're not related to each other. This is going to be independent. And for independent, remember we run this as a 2 mean problem. And then we're always using T's for means. H0, H1. Because it's 2 means, I should have 2 mean symbol. H0 is easy, it's always going to be equals. H1, let me label what 1 means and what 2 means. 1, let's call that my treatment group. And then 2, let's call that my control group. And the question is, what symbol goes in the middle? Less than, greater than, or not equals. So back to the question, it says, can you conclude that the mean recovery time for those receiving the treatment is less than the mean for those receiving the standard treatment? Standard, remember we said was the control. So the controls receive the standard. Standard is the controls. So the question is saying, can you conclude that the new treatment is less than the control? So treatment less than control. Treatment less than control. Example 4. A statistics student heard that an individual's arm span is equal to the individual's height. To test this hypothesis, the student used a random sample of 10 students and obtained the data below. Does the sample provide evidence to contradict the belief that an individual's height and arm span are the same? In other words, can you conclude that an individual's height and arm span are different? First question, is this independent or is it matched? Based on the way that the table is formatted, it makes it clear that these two measurements go with student 1, right? So this is the height and arm span of student 1. So these are two measurements on the same student, right? Two measurements on student 2, two measurements on the same student 3. So this is a typical match situation. And for matched situations, we run this as a one mean problem. And then we're using t's because it's mean. And for one mean match situations, what we actually do is you're going to subtract, right? You'll subtract height minus arm span. You'll find the differences. And that's your one sample that you'll work with. Part A, H0, H1. Because we're running it as one mean, we'll just have one mean symbol. The match situation, you're always comparing it with 0. H0 is always going to be equals. H1, less than, greater than, or not equals. This is the tricky one. But in this one, it's not that tricky because we're asking, can you conclude that an individual's height and arm span are different? Different, that's automatically going to be not equals. The tricky one is deciding whether it's less than or greater than. But here it's different. Difference automatically going to be not equals. Example 5. To test the belief that sons are taller than their fathers, a student randomly selects 10 fathers who have adult male children. She records the height of both the father and the son and obtains the following data. Are sons taller than their fathers? First question we need to ask ourselves is this independent or matched? Okay, for matched, the two common situations are you were taking two measurements on the same person, or if the people in one group are related somehow to the people in the other group. In this case, the people in the father group are related to the people in the son group. So these are actually father-son pairs. So they actually should go together, which means this is a match situation. Which means we'll run this as a one mean. And then we're using t's, of course. In a match situation, your next step will be to subtract and find the differences in Google Sheets. Part A, H0, H1. This is a one mean situation, which means I should have just one mean symbol. And match, you're always comparing it with 0. H0 is easy, it's always equals. H1, less than, greater than, or not equals. So this one is going to be a little bit tougher because it's not going to be the not equals. Sons taller than their fathers. For the match situation, don't get tricked by the question. So it says sons taller than their father, so you may be tempted to say greater than, but be careful. For the match situation, what I recommend you do is actually enter the data, find the differences, and then find the mean and the standard deviation. If the mean is positive, that suggests that this is going to be greater than. If the mean is negative, that would suggest that this is going to be a less than. Okay, so that's the kind of the cheating way to do it. The correct way to reason about this is to write down the father and son. So write down father and son. And write down what symbol should go in the middle based on the question. Sons taller than their fathers. So what symbol would go in here if the son is taller? Sons being taller than their father would be that symbol. Okay? Sons taller than father. Or sons being taller than their father, the same thing as saying that the father is shorter than the son, which is a less than. And then what you're actually doing is you're moving the son to the left side, so you're subtracting sons. To get father minus son is less than, and son minus son is 0. Father minus son is exactly the differences that we're computing. So this is really less than 0, which is why this is going to be less than 0. But once again, another way to check is to actually do the calculations and look at the mean of the differences. If it's negative, it'll be less than. If it's positive, it'll be greater than. So when you do this, my guess is that the mean here should be negative, which is going to match this less than. Example 6. Do people tend to spend money differently when using a credit card compared to cash? The following data shows a random sample of credit card purchases and a random sample of cash purchases. Is there evidence to conclude that people spend money differently when using a credit card compared to cash? Question, is this independent or is this matched? So you may say that these are credit card and cash purchases from the same person. If that's true, this would be matched. So if this is a credit card purchase and a cash purchase by the same person. But if you read the question nowhere in the question does it say that that's what's happening here. Nowhere in the question is it saying that this is credit card purchase and cash purchase from the same person, right? All it says is random sample of credit card purchases and random sample of cash purchases. So for all we know, this could be different people for the credit and different people, a totally different group of people for the cash. So nowhere in the problem does it make it clear that these are purchase amounts by the same person. So this will be independent. Which means this is a two-mean situation. And we're using t's, of course. H0, H1 should involve two mean symbols. H0 is always going to be equals. H1, less than, greater than, or not equals. Back to the question, is there evidence to conclude that people spend money differently when using credit card compared to cash? So differently, not equals. Have a great day, and I will see you in the next one.